So here we will try to learn the mathematics of single slit diffraction. So we have this slit which has a size of opening A. Okay, width of this slit is A, and we call the distance between this slit and the screen to be L. Okay, and here now we will compare this with the case of the double slit, which we already learned. And in the case of double slit, it was actually easier because we had only two very narrow openings. So we could consider only two light paths and exactly figure out the condition for both the constructive interference and destructive interference. But here in this single wide slit, there's a pretty wide opening. So the light waves are passing through wide area. So which means there will be many light rays we have to consider. So well, it is clear that at the center it will be the brightest. Okay, but then how about other positions? It is very difficult to figure out where all of these light waves will constructively interfere. So therefore, well, in a short way, I can say that we don't really have to find the constructive interference condition. We will only find the destructive interference condition and see where dark bands will appear. Okay, so how we do that is like this. We first try to divide this slit opening into two sections, upper section and lower section, and then let's consider two light paths, one coming from the upper edge of the slit or the upper edge of the upper side, and then the other coming from the middle of the slit. Okay, and then when they arrive at the screen together, they will form a triangular shape like this. But then now again, let's try to remember what we did in the case of double slit experiments. When you try to explain double slit using mathematics, we made one important assumption. Well, what was that? Can you remember? We made an assumption that the distance between the slit and the screen was much larger compared to the distance between two slits. And then do you remember why we did that? It is because if we assume that the L is much larger, then these two paths become almost parallel to each other, and then we can redraw a shape like this. Then it will be easy to figure out the path difference. Okay, so we will use the same idea here, and then assume that now this time L is much larger compared to the width of the slit. Okay, now in this case, again, we are not going to find the condition for the constructive interference, and we will try to find only the condition for the destructive interference. Okay, how we do that? We first have to figure out the path difference. Okay, so here these two paths, what is the difference between them? Okay, in this figure, this much is the difference, and then this line is perpendicular to one of the paths. Okay, and then let's call it delta x. And what is delta x? You can use the simple trigonometry and figure out that this is equal to half of a multiplied by sine theta. Half of a is of course this much, because this is the upper edge and this is the middle of the slit, so therefore it's half of the a. And then what is theta? Theta is actually the angle between the direction going into the central part and the direction of the one of the path. Okay, so this was theta. But then by using simple geometry, you can easily figure out this angle is also theta, right? Okay, so therefore this delta x will be half of a multiplied by sine theta. Okay, and then what will be the condition for the destructive interference between them? Of course, if this path difference is equal to half of the wavelengths, then when they arrive at the screen, these two light waves will be pi difference, have a phase difference in pi, or exactly shifted in phase with each other, exactly off phase. So therefore this is the condition for the destructive interference between these two light waves. Okay, and then how about many other light waves passing through different part of the slit? Now since we have divided into two slits, you can move down this slit and then keep finding two light waves or pairs of light waves satisfying the same condition. Okay, for example here, these paths written drawn by red color, they are separated by the same distance, exactly the same distance like these pairs of green rays. And then same thing for this purple, and also same thing for this blue, same thing for this yellow. So for example, between these two yellow lines, you can still draw this perpendicular line and find that this much is exactly delta x. And then if this L is much larger than A, then actually angle becomes all the same. So therefore, what we can finally conclude is that at this condition, all of the light rays going through this slit will form pairs which can satisfy the complete destructive interference condition. Okay, so this will be the position for the first dark band. So in the middle it will be very bright, and then if you move away and then satisfy this condition at this angle, you will see it is very dark. Okay, and next, can you find another or other conditions where the destructive interference will occur again? Now, instead of dividing the slit into two sections, let's try to divide into four sections, just like here. And then now we only have to consider four light rays. Then if these two upper rays satisfy destructive interference condition, and same thing will happen for the lower two. So therefore, now we can rewrite that now we can find the same condition. Okay, how about the path difference between these two? Now this path difference between these two rays is not half of A multiplied by sine theta, but quarter of A multiplied by sine theta, right? Okay, and if this is again equal to half of wavelength, that will be the condition for the destructive interference. And by moving down this slit, you can keep finding pairs of light waves again satisfying destructive interference. This is the condition for the second dark band. And then you can keep dividing this slit into even number of sections, like 6 sections, 8 sections, and apply the same condition, and then find, okay, these are the conditions for all the destructive interference conditions. Okay, so we have these even numbers 2, 4, 6, 8. Okay, so if you multiply the equation by these numbers, you can find that these even numbers, the factor 2 drops out because of these 2. Okay, and then finally you can summarize that this condition can be written using a single equation like this: A multiplied by sine theta is equal to M multiplied by lambda, and this M is just an integer like this. And here, this is one thing you have to memorize or remember: there's no zero. You know, in the case of double slit interference condition, double slit case, there the dark fringe, I'm sorry, in the case of a double slit experiment, the condition for the bright fringe or constructive interference will look just like this. And then there it included 0. But here, now this is the condition for the dark fringe because of the destructive interference, and here you have to exclude 0. Okay, so finally the figure will look like this. This position is a central position, it corresponds to 0, and then this position is 1, 2, 3, and then same thing for the other side, 1, 2, 3. Okay, so only at the integer positions without 0 will correspond to a dark fringe in the case of single slit diffraction, but in the middle, which is 0, it will have the brightest position. Okay. So we just learned that in the single slit diffraction case, the condition for constructive interference doesn't really exist. So we learned only the destructive interference condition. From there we learned that this dark band appear at regular interval except the middle of the screen where it becomes the brightest. Okay, and here of course we will now study the intensity of the single slit diffraction with more detail. And now situation is actually a bit more difficult compared to the Young's double slit experiment, because in Young's double slit case we had two narrow slits, so we had to consider only the interference between two light rays, so it was simple. But in this situation of the single slit, we have a wide opening like this, so therefore the large area of wavefront will pass through together, so the mathematics is a bit more difficult. So we will do it in two steps. First, we will discuss it qualitatively in this slide without using much mathematics, but then in the next slide we will finally use the mathematics to describe it correctly. And in doing so, we will also use the phasor. Okay, do you remember what phasor was? Phasor was just like a vector which is fixed on the origin and then at the same time rotate like this. So if you maintain the length of this arrow, the projection along the vertical axis was just like a sine wave. So it was convenient to represent wave, and at the same time it was particularly useful when you try to combine many of them because it works just like a vector. Okay. So based on this idea, now we will use phasors, and for that purpose we will try to divide the slit into n zones of equal width delta y. So just like this. So we will divide into 1, 2, 3, 4, 5, and so on, and n zones, and then the width between each zone is delta y. Okay, this is what we call, and then each zone will produce a wave or phasor. Okay, and then now let's try to select two waves or phasors adjacent to each other, and then what will be the phase difference? If you of course know the path length difference between two waves and then divide it by lambda, which is wavelength, and then multiply by 2 pi, then you get the phase difference, right? Because each wavelength corresponds to 2 pi in phase. And then what will be the phase difference between these two light waves when you are at an angle theta with respect to the central position? Of course, try to remember what you learned in the previous slide, and of course in this case it will be delta y multiplied by sine theta, right? Okay, so therefore the phase difference we call delta phi can be written this way. And of course now from here, this delta phi actually means something like this. If one phasor is here and then the second phasor is here, then the difference in their angle, this will be delta phi. And of course when you combine them all, you can combine them just like vectors. Okay, this is the idea. So at the center of the screen where theta is 0, then in this case of course delta phi will also be 0, so therefore all the phasors are pointing along the same direction. So if you combine them, it will make a long straight line, so the intensity will become maximum because the amplitude of the phasor becomes maximum, right? Okay, and then how about at angle theta, which is larger than 0? In this case of course delta phi will also be larger than 0, and delta phi corresponds to a small difference in angle between these two phasors and also between these two, so it is constant, so the phasors form an arc like this. Okay, so then when you combine them, you get the total net amplitude just like this. This is a long arrow but still smaller than the total length of this arc, right? So therefore amplitude has become slightly smaller, so intensity has decreased a little bit. And then let's try to increase angle theta a little bit more, then probably you will have some shape like this. The phasor will form circle like this, and then if the final phasor is here, your amplitude will be something like this. So this amplitude is smaller than that, so amplitude has become decreased, so the intensity also has decreased. And then if you still continue to increase the angle, then you will certainly arrive at a stage where you make one full turn and the final phasor arrives at this position, which is origin. In that case, of course, the net amplitude is 0, right? So therefore, the intensity will also become 0. This is the condition for the first dark band. Okay, this is where we observe no light. And then let's continue to increase the angle again. Then you will get the phasors like making one full turn, and then has to go more. This will be the final phasor, so your total amplitude will be like this. This is not 0, but still much smaller compared to this one. So, and then here, of course, you can naturally understand why it has become smaller. And then let's continue to increase again. Then you will arrive at the stage where you make 2 full turns like this, and then the final phasor comes back to the origin. So then this will be the condition for the second minimum or second dark band, like this, right? Okay, and then continue to go. So this basically explains why the intensity decrease as you go up to a higher angle, and from time to time you come across the dark band. Okay, this is exactly the situation that we are going to explain using mathematics in the next slide.